the ball is, see, the spring is coiled, right? And the ball is right there. Hasn't moved yet. That's time 0. Now at time 1, let's say that the spring has sprung, right? So it's uncoiled. The ball is moving, right? It's got some v1. I'll call it, so the subscripts here represent the times. That's just the notation I'm choosing. So v sub 1 means the speed at time t1, right? And then at t2, right? Now the ball has, so the spring sprung, the ball has flown out to the side and hit the table, right? So right before it hits the table, we want to know what's its speed. So here's v2. So in fact, we're being asked, what is v2? Like, that's the question, right? And what are we given? Oh yeah, we're given, let's say that we're told, well, actually, we're told the physical situation. Do we know v1? I should say, do we know v0? Yeah, we know v0. v0 equals 0. We also know the height. So we know this height is, we call it h. So we know h. What else do we know? We know mass of the ball. Although, is that going to matter? Probably not. Never does from. What else do we need to know? We also need to know how much the spring is contracted. There's some potential energy in that spring. It's going to get converted into kinetic energy initially, and then other things happen, right? So let's call that L, and we'll just say this is just, L is just some length. It's essentially just delta x of the spring at time 0. That's how much the spring is compressed at time 0. Okay, so we're given all those things. Great. So now we can go ahead and plug all this stuff in, right? Oh yeah, and we're assuming there's no wind resistance or friction or whatever else. So let's do that. So now I've got and I'll try to do what I didn't do last time, which is just strictly and in a very disciplined manner, pay attention to my subscript. So I want final over here, initial over here. And that equals work net external. And my system consists of just the ball, right? Oh, and what times am I talking about? So I put final initial, but now I've got to make some decisions. I've got 3 times in the problem. So let's go from time 0 to time 1. All right? So this is time 0, and this is time 1. So final initial really isn't, that's generally true, but to put specific values in, I've got to be really clear about what I'm going to consider to be final initial time in the problem. So great, what do we have? We have kinetic energy, that's 1/2 mv at t1 squared. Oh, yeah, that's right. And we add to that potential energy due to the gravity. What is that? Well, at time 1, it's actually up at h, above the ground. And just like last time, let's go ahead and define the ground to be potential energy of gravity equals 0. So let's just call the ground equals 0. That means that we have a non-zero potential energy here. What is it? Is it positive or negative? Positive. It's mgh. And at time 1, what's the potential energy in the spring at time t1? Well, the spring has sprung by time t1. Spring is, right, it's back at its equilibrium position. So somebody might say, wait a minute, the spring was coiled up at time t0. It opened up, but maybe it's reverberating or something. Well, if that's true, that means that not all the potential energy in the spring actually was imparted to the ball. But what we usually assume in a physics problem like this, unless it's otherwise stated or unless you have, you can also, if you have a strong opinion about it, you can go ahead and do a more complicated calculation. But generally what we'll assume is that all the potential energy in the spring was imparted to the object that was sprung away, and that the spring is ideal in some sense, that we can neglect its mass. In the same way that we neglected the mass of the string in this pendulum a minute ago, we'll neglect the fact that the coiled up piece of metal in the spring actually has its own mass. We'll assume it doesn't have any mass, or that it's negligible compared to the mass of the ball. So that means that the potential energy in the spring that you had from compressing it, essentially all that potential energy gets imparted to the ball. All right? So if you assume that, then we get for right here we have 0 for the potential energy of the spring. Now I just started writing down terms without labeling each of them. Maybe I shouldn't have done it that way. Maybe I'll do this to make it clear if you're looking at this. So I'll say potential energy spring, and I'll say, oh, but that's 0 at time t1. Okay, just to make it clear where that came from. Great. So I've got my terms here. What about t0? Well, I've got 1/2 mv naught squared. But what is v naught? 0. It's not moving. And then I've got, again, mgh, right? It has the same potential energy as the potential energy due to gravity didn't change from time 0 to time 1. So let's go mgh. Now we've got a non-zero. This is the earliest time in the problem, right, when the spring is all coiled up. So there is potential energy. We have an equation for that. Didn't give myself quite enough room to do this. It's 1/2 k. Oh, and I have to be told that, so that's another given. In the problem, they better tell me what the spring constant is. Or if they don't, that's something I have to solve for some other way, some other information. But let's say they tell me what the spring constant is. So it's 1/2 k delta x squared. I'll give a name for that. We call it L, so L squared. Great. Do all of that equals W net. So the only forces acting on the ball during this period are spring, gravity. You might also worry, well, wait a minute, it was initially sitting at time 0. It's inside. It's being supported by a normal force. It wouldn't do any work anyway, actually, because the ball would be moving in that direction. But generally, the way I'll think about it is that I'm looking at the time right after the spring has been released, and let's assume there's nothing else touching the ball to make our life easy. So the ball initially is the only forces acting on it are spring and gravity. So there's really nothing left to give us a work over here. There's no friction in the problem, no other forces. No one's pushing. I'm not putting my hand on the ball when I shoot it. Right? So we'll just say that's equal to 0. Okay, great. So now what do we get? Did I do it right this time? I think I did. So this is all for time 1. This is all for time 0. When all the dust settles, we find that mgh there cancels with that mgh over there. Right? Those just cancel out. So when we go from t0 to t1, what we find is that 1/2 mv1 squared, right? And like that cancels out, it's subtracted, equals 1/2, let's get the minus sign there, it commutes in there, so 1/2 k L squared. In other words, what we find is that the potential energy that was initially in the spring got converted into the kinetic energy that at time t1 is in the ball, right? Not a huge revelation, but that's where it comes from, right? And gravity didn't play a role because it didn't change its height. Now when we go from t1 to t2, what happens? When we do that, now we have the same equation we write out. Say, all right, well, we've got, this is so now our final time is t2. Now our initial time is t1. Once again, it's going to equal 0 because there's no other forces other than gravity. In fact, there's no spring force anymore, right? The potential energy due to the spring, right, is going to be 0 here, and it's going to be 0 here. Right? So that's not going to play a role anymore. But now what's changing is the height. And other things are changing too. The direction of the velocity is changing, right? But we don't care about direction of velocity with the conservation of energy equation. That's what's beautiful about it. We can ignore that. All we care about is the kinetic energy term. So when we get that, we get 1/2 mv2 squared. In fact, that's what we're looking for. V2. That's the final. That's the velocity when the ball hits the table, right? Excuse me, actually speed. We use the speed hits the table. That's what we want. And we add potential energy due to gravity. But at time t2, what's the potential energy due to gravity? 0. It's at the bottom. 0. Great. I love when there's zeros. So now we've got 1/2 mv1 squared. So notice that I didn't solve for v1 up here. I could have. And get a square root of a bunch of jazz, right? But I sort of thought, well, yeah, but I think it's going to show up again. So I'm just going to leave it in this form, and maybe it'll magically cancel out. And it will. So I have 1/2 mv1 squared, right? And now I can add potential energy due to gravity. What's that? I think it's mgh at t1 still, right? Super. So I think that's correct. So now what I get is an equation that says, oh, the kinetic energy, 1/2 mv2 squared, at the end of the whole process, these are equal to 0, is equal to whatever the kinetic energy was at time t1, plus, yeah, because the minus sign on the other side, it goes away, so it's plus, good, mgh. I think I got my signs right. The final kinetic energy at T2, right, is greater than the kinetic energy at T1. Makes sense, because it's lower, right, just like in a roller coaster. But I don't know V1. Oh, yeah, I've got an equation for it. In fact, I've got an equation for 1/2 m V1 on my smart squared, so I can just substitute that in. So what do I get? I say, oh, yes, the final 1/2 m V2 squared is, what is this? This is just the initial potential energy of the spring, which was 1/2 k L squared, and now I can add it to 1. Oh, great, so now I've got the answer written out in terms of things I know. I know this, I know this, I know this, I know this, I know this. And notice that m doesn't cancel out here, because I specified the amount of potential energy in the spring in terms of k and L, because it depends on the mass on the end of the spring. It only depends on how much it's compressed. So here's a problem where the final answer will depend on the mass of the object. And think of how that will happen. If the object is really massive, right, it says that you're going to get a smaller velocity as a result for the same amount of energy in the spring. But that makes sense. Put a big, massive bowling ball right on the end of a little spring, it's not going to be moving very fast after the spring goes. So it should depend on mass. That's good. So often in this class, masses are going to cancel, because in a lot of cases, we're only going to have a normal force, which depends on its weight, usually, which is a mass-dependent thing, and the force of gravity, which, again, is exactly its weight. So if all the forces in the problem depend on mass, the mass cancels out, right? But in this case, it doesn't. Okay, great. So then if we want to solve for this thing, okay, what happens? We say, yeah, V2 is square root, and okay, I'll just write it out. You get 2, so this half goes away. You get 2 here in front of that guy. Oh, and the mass goes, so this mass is down. So you get 2gh here, and you get k over m L squared. Does that look right? I think I got that right. Let's see if the units make sense. This is a length squared. That's a mass. Oh, what's k? What's the units of the spring constant? Well, spring constant is like this. So that means that the units of k are the same as the units of force over the units of length, right, over meters, and that's kilogram meter per second squared meter. Oh, the meters cancel, so it's kilograms per second squared of all things. So if I have kilogram per second squared, kilograms cancel, that's inverse second squared times the length squared, it's meter squared per second squared. Square of that is meter per second. You had to go around the horn to solve that, but anyway, it turns out it's a velocity. So good. This, I think I got my algebra right. And then for this guy, I got meter per second squared, and that's meter per second squared. Yeah, squared, that's velocity. Good. So the units make sense. One thing I should point out too is that, well, let's check a couple more things. So one thing we already checked is that the bigger the mass is, the smaller the velocity is at the end, and that's right. That's certainly true. And sure enough, mass appears in the bottom here. So this guy goes away. Notice that it doesn't affect this term. Why is that? Well, because if the mass is really big, right, then the spring doesn't wind up giving you a lot of velocity at time v1. It's hardly moving in the horizontal direction, right? But you still fall distant h, and I don't care how massive or unmassive the object is, it's going to be moving the same speed at the bottom of a fall of h, height of h, right? So this doesn't depend on mass, as it shouldn't. But this has the dependence I was sort of expecting for the spring. What else? The more I compress the spring, L is how much I compress the spring. The more I compress it, the more kinetic energy I'm going to get out of v1, and that's reflected here, right? And you get more bigger v2, right? One thing is, so this is in the form of the square root of a sum of two things, right? That's what we would have gotten if we used Pythagorean's theorem for the direction of the velocity, if you calculated the velocity and the x direction of the y and stuff. Well, this sort of comes out automatically by doing conservation of energy, right? You never had, at no point in this problem did we have to think about which way is the ball moving. All we had to ask was, how fast is it moving right now, and plug that into 1/2 mv squared for the correct moment in time. So it's sort of magic, right? Things sort of get figured out automatically in a magical way. That's why physicists like conservation of energy, right? Well, they like it because it's true, but they also like it because it's a powerful calculational tool. You can get away from vectors, think about numbers, like the speed, instead of worrying about the direction of the velocity. It's really nasty. Doing equals ma on that roller coaster, or for that matter, on this problem is projectile motion problem is simple, as we saw, because we can decouple x and y. But if we had some crazy ramp, suppose this thing shoots out from a spring and then it goes down and it lands on a ramp for a while, it's friction free, and it's going up and down some crazy profile, or whatever it is, it would be the same calculation. We would, at the end, if we just know how much change there is in the height, we'd calculate it. And if the height's the same, get the same formula out, it'd be just as easy to calculate. So it's a really powerful notion, even though it doesn't solve everything. It doesn't say how long it takes to something out. Okay, great. One thing I want to point out too is that I think the way I solved this was a natural way for most new students in physics to think about the problem. You think about what happens in the transition from time zero when the spring is compressed to the moment that the ball's moving and the spring has lots of energy, but it hasn't fallen yet. The ball's still at the same height. And then you calculate, the extra change that happens because the ball changes its height and the potential energy to gravity plays a role, right? But you don't have to do it that way. You could just say, this is the way I would, like if I were on a test and I've got 5 minutes left, no, I'm not going to do it this way. I'm just going to skip to the chase. Conservation of energy, it doesn't tell you what times you have to use. It works for any pair of times. As long as you know as long as you know what all these things are, you can write the equation down and solve it, right? The equation is valid for any final time and any initial time. So I could have just said, well, let's make this time 2, right? So time 2. Let's make this time 0. Skip T1. Who cares about T1, right? Let's see what we get if we do that. Well, at T2, I get 1/2 mv2 squared. I get mgh. But potential energy to the gravity at time 2, that's 0, right? It's already all the way on the ground, right? Potential energy to the spring over here. That's already 0. The spring's already sprung by T2, and there's no potential energy left in the spring. If we go to T0, now there's no kinetic energy, right? At T0, kinetic energy is 0. The potential energy to the gravity, though, is non-zero. It's mgh, right? And the potential energy to the spring is non-zero. All the way back at T0, it's compressed. So it's 1/2 k L squared. And this is a single equation that only involves things we know and the thing we want. In other words, there's no V1 in this equation. When I solve this thing over here, if I didn't think ahead, I would have solved for V1 after I did this, and V1 equals square root of the big nasty thing, right? And then I would have had to undo that and square it and put it in this other, and eventually it drops out of the problem. But if we from the outset decide if all I care about is the final velocity of the ball, the final speed of the ball, V2, I mean, and we know a bunch of stuff about V0, who cares about V1? I could have described, in other words, we could have done the problem in even a crazier way, where we calculated, from this time to this time, and then from this time to this time, and then from this time to, right, and then break it up into tiny little increments. We could do that. We get the same answer, but it would take a lot longer, and it's not going to help me get to the last problem by the end of the exam. So the way to do it is to figure out the times that are most useful for the particular question you're being asked to solve. If you go ahead and write down, oh yeah, and this is 0 for the same reasons that it was 0 individually, and they'll go to this equation, same thing here. And so we wind up with 1/2 m v2 squared. You just read it off from the equation that's up here, right? And this is a minus sign, minus sign equals mgh plus 1/2 k L squared. That's the same equation we had. You multiply by 2, divide by m, and take square root, right? So it's faster if you think of which times to take. The thing about this problem is just like all the problems you see in this class, and what you're going to see in the future, right? Your best ally against, in the fight against errors, right, is having a good idea of what makes sense as you're going through anticipating what the results will look like. That can get you in trouble too. If you have the wrong intuition, you won't believe your answer, and you'll put a minus sign where it doesn't belong and not catch it or whatever. But for a problem like this, you saw me balling up, initial and final. That's why I'm trying to be so pedantic about these subscripts. But I always think it through at the end, like, should the velocity be bigger or smaller? And you know the answer in most cases these sort of problems. You can sort of figure it out. So anyway, you should have some idea where it's going, and the more you do stuff, the more you have a good feeling for that. So in the minutes that remain, maybe I'll mention one more topic. So I did the cartwheel thing I didn't actually do a part really, I used my hand to demonstrate. But we talk about static versus kinetic friction. I mean, it's that when something is rolling without friction, it's actually not a kinetic type of, rolling without friction. Rolling without slipping is what I meant to say. So a wheel is rolling without slipping, right? There is friction. There's friction in the form of, or potentially friction. Friction in the form of well, which is it, static or kinetic? Static. And actually, think about it for a second. If I have a wheel rolling this way, and it's not speeding up or slowing down, it's just rolling. It's hard to do because this wheel's so skinny, it doesn't want to fall over. But if it's moving along at a constant rate, in that case, you don't actually need any friction. But it's on a ramp where it's accelerating faster and faster down the ramp. That's the case where you really need to have friction from the ramp onto the wheel. Otherwise, it would just slide down. If there were no friction, suppose you put a wheel on a ramp, and there's no friction of any kind, no static friction at all, right? It would just slide. There'd be nothing to make it roll. The only reason why things roll from a standing start is that some frictional force on the ground is keeping it from just sliding, right? So it rolls. And if we ask the question, and I told you guys, we demonstrated a little bit with, using my hand with the cartwheel simulation about why it is that the thing on the part that's touching the ground is not moving momentarily. Another way to see that is to take this guy and put a piece of chalk on it and then see what, whenever I see a chalk next to a wheel, it makes me think of the parking tickets and stuff. But the idea here is to move the chalk with the wheel and see what path is traced out by this part of the wheel. It's kind of surprising the first time you see it, I think. So I'll just do it right here. We'll just roll it along. And what we'll see is that when the chalk gets close to the ground, it's not moving sideways. It's only moving up and down, and momentarily it's still when it's the ground. So it comes along. All right. Hits the ground right there. So now it's touching the ground. That's where friction is acting on this part of the wheel. Now it keeps going. Oop, am I dropping it? Up. All right. So that's the shape of it. And around out of space. So that's what happens. I didn't do a perfect job on the side. It should have been like this. Like that. Kind of balled it up in the very end. But what you see is you get a particular shaped curve, and the curve gets infinitely steep right at this point. In other words, the wheel is coming straight down to the ground. So when a wheel's rolling, this part of the wheel, as it's approaching, it's getting almost to its moment of glory when it's actually on the ground, helping the car not slide off the road, it comes straight down to the ground, comes right down, and then lifts straight up. It never goes sideways, which is kind of surprising the first time. It is to me. It's surprising. It turns out the shape of this curve is important. It's got a name. It's a cycloid. It has other nice properties that you learn about in these classes. But anyway, so that's just another way of seeing this fact that you're going to need to rely on. Rolling without slipping falls under the static friction category. And how much work does static friction do? Does it do negative work, positive work? Zero. Never. Static friction does not do work. So that's important. All right. We'll see you.